This is Frank. Frank changed the RTL for one field in one register, and he didn't tell anybody. That caused the software on the chip to stop working, which caused the drone it was controlling to crash into the home of someone who got a bit irritated. We interrupt this commercial to bring you this important message. It has come to our attention that many design teams suffer from non-automatitis or scriptophobia. These have been known to cause headaches and respin regurgitation. If you experience these symptoms, contact Semaphore for a no-obligation checkup. You don't have to suffer. Reach out to Semaphore. We now return to your regularly scheduled commercial.
Well, that's cool. I don't know how to top that, but hello everyone. Welcome to the formal verification session 2. I'm the session chair for the session. So my name is Xiaoling Chen. I do have a true passion for formal technology. I've been in this field since I was first introduced to it many years ago. I'm currently working at Synopsys as the director of applications engineering and to support VC formal product. So there are 4 paper presentations in this session. So during the presentation, please feel free to type in any questions you have in the chat box. At the end of the session, we will have a live Q&A with the authors, with the speaker, and I will read out the questions and moderate the talk. Without further ado, let me introduce our first speaker. His name is Ping Yang. Ping came from Oski, and Ping is the principal engineer at Oski Technology, which has since been acquired by NVIDIA. He has over 25 years of experience in application marketing and product development. He worked on all major EDA companies, including Zero In, Synopsys, Mentor Graphics, Siemens EDA. So he's very familiar with assertion-based verification, formal verification, and clock domain crossing verification. Today, Ping is here to tell us how to sign off with end-to-end checking methodology. So please welcome Ping.
Welcome to DVCon 2022. In this presentation, we're going to talk about rising the level of formal sign-off with end-to-end checking methodology. This presentation is based on the experience of Oski Technology. For the past 10 years, Oski is using this end-to-end formal checking methodology to verify some of the most complex blocks in the customer's designs. For the agenda, we're going to start with the formal verification usage level. Then we're going to introduce the end-to-end checking methodology. There are 2 very important components with the end-to-end checking methodology. One is the end-to-end checker, another one is the abstract techniques and modeling. And then we're going to conclude the presentation with 3 test cases, and we're going to summarize how we verify them using this methodology. Let's take a look at the formal verification usage level. There are 5 levels of formal verification: level 1, 2, and 3. Auto formal, formal apps, and assertion-based verification formals has been supported well by EDA vendor. Level 4 introduced block level formal sign-off. It replaced block level simulation and used formal verification to verify the design exhaustively. So level 5 formal verification focusing on specific system level requirements. Now in this presentation, we are going to focusing on level 4 formal verification with end-to-end checking methodology. The goal is to use end-to-end checkers to capture the design specification, and then formal verification can be used to verify those checkers exhaustively. Some users have asked what are the differences of this block level formal sign-off approach. So first of all, is it different from traditional assertion-based formal verification? It is a black box approach. The end-to-end checkers are developed based on the specification. It does not depend on the RTL code. It does not use any RTL signals. Hence, it's not constrained by how the RTL code is written. So we can use multiple formal test bench to verify the design, and each formal test bench can focusing on a particular section of the design or a particular functionality. This approach has multiple benefits. As the checkers are developed based on the specification, it can identify incomplete or ambiguous details in the specification. It provides clear value to the project team because the checkers map directly to the functional specification, and they can find bugs early in the design cycle while the designers are still coding. In addition, as the verification is done completely based on the specification, it can replace simulation completely and sign off the block formally. Now, during the formal process, as we are refining the checkers and constraints, it can find deep and corner cases issues. And after a bug has been found and fixed, the formal test bench can be used to confirm the RTL fix has resolved the bug completely and ensure that all the bug scenarios has been addressed. Finally, for reuse, the formal test bench can be reused to verify new RTL code. To enable block level formal sign-off, we have developed the end-to-end checking methodology. This methodology has been developed and refined for many years. It guides management and users through the phases so that important details are not missed or skipped. The end-to-end checking methodology consists of 3 phases: the planning phase, the implementation phase, and the closure phase. Now, management support is essential to make formal verification successful. Although, as it has been emphasized before, we want to mention a few items explicitly. First of all, we need a team of formal expertise and engineers. Formal expertise are very important for the formal planning process. We want to make sure that the formal test plan will be executed and implemented correctly. Formal engineers are required to implement the formal test benches. We want to make sure that the formal engineers are embedded into the design team so that they can understand the design requirements and they can communicate issues back to the design team as soon as possible. Now, finally, for formal closure, we will need compute resources, server farm environments to verify all the constraints and properties as deep as possible. And if we encounter some difficult properties, we want to get help from the vendors. During the formal planning phase, we want to have formal expertise with a lot of experience to help us with the following tasks. First, we look at the blocks in the design. We want to identify the blocks that are suitable for end-to-end formal checkings, and we evaluate them and to determine the effort required. Then for each of the blocks, we describe the end-to-end functionality that need to be verified. We prioritize them based on their importance and risk. Now, for some of the complex properties and functions in the design, we can take a divide and conquer approach. We can map them to one or more formal test benches. If we are early in the design cycle, we can partition the block explicitly into submodules or use a virtual approach with system verilog bind statements. During the formal implementation phase, we allocate formal engineers to work side by side with the designers. Now, for each of the blocks in the design, we start by capturing the interface properties as constraints or assertions. Now, if we engage with the design team early in the design process, the end-to-end checkers will be developed side by side with the RTL code. It provides early feedbacks on the correctness of the design and also ensure its qualities. Now, for some of the complex structures in the design, abstraction models and techniques are used to short-circuit the depth of the design and also reduce the state space for modifications. Now, during the formal closure phase, the goal is to ensure all the test bench has reached sign-off quality. Now, for each block in the design, we want to make sure we did not over-constrain formal analysis. So we can validate the formal constraint using simulation to make sure that they are correct and sufficient. Now, we want to make sure that we have proof and debug all the end-to-end checkers to make sure that they are conclusive. If they are still inconclusive, we want to make sure that the bounded proof are deep enough or they have reached the required proof depth. So finally, we want to make sure that we have examined the formal coverage is sufficient. Similar to simulation coverage, we can measure formal coverage using line, bench, stay, and transition coverage. Cone of influence coverage can be used to ensure there are sufficient checkers inside the design, and formal cone coverage can be used to measure how much formalization has exercised the design. After going through the end-to-end checking methodology, now we want to take a look at 2 important components. One is the end-to-end checker, another one is abstraction technique and modeling. First of all, let's just take a look at the end-to-end checker. So the end-to-end checker was developed using the design specification. It is like a reference model to the original design. So sometimes developing the checker could be as big an effort as writing the RTL code. So on the left-hand side over here, we have an RTL block. So the end-to-end checker will monitor the input to the RTL block and the output to the RTL block. A protocol monitor will be used to constrain the input side and then another protocol monitor will check the output side of the design. The monitor will also be used to extract data from the input stimuli, and those data will go into the checkers. Now, the checker will perform similar operation just like the RTL blocks, so it will compile and store the expected result. So once the data is available on the output of the RTL block, we will extract the data, and then we will compare that with the originally pre-computed result, and make sure that the RTL block is performing the operation correctly. Now, on the other hand, if we implement the checker just like the RTL block, the checker will be as complex as the RTL blocks. So that's not very good. So as a result, while we are developing the checker, we will look for ways to simplify the operation of the checker. And at the same time, we will deploy abstraction technique we will talk about in the next sessions. Now, for the checkers, we purposely divide the checkers into 4 parts: the input handshake, the output handshake, the control path, and data path. Now, one of the reasons for doing this is allow multiple team members to work on a different part of the checkers concurrently. But much more importantly is by doing this, we can deploy different formal algorithms and approach on different part of the design. So for example, we can first focusing on the data path of the design. So we can use a special formal algorithm to verify the data path of the design. And then when we are verifying the control part of the design, we can black box the data path elements inside design. So this enables us to handle much more complex design and also enable us to do a divide and conquer approach. Now, in addition, abstraction model can also be used to simplify the design. So for example, if there is long latency elements or storage elements inside design, such as counters, FIFOs, or memories, we can use abstraction model to replace those components and simplify the formal models. Next, let us take a look at a few abstraction techniques. First, case splitting. Case splitting is more like a divide and conquer approach. It decomposes a complex design into multiple formal runs, and each formal run will focusing on a particular configurations. So as a result, it reduces the cone of inference and the state space of each formal run. Cut points and black box are very common and very popular. It eliminates logic driving the cut point and also the logics inside the black box. These cut points and output of the black box becomes control points for formalifications. We cannot constrain them accordingly. Next, resettable registers and counters. Now, they are very common elements inside a design. However, sometimes it may take a lot of transactions to load an interesting value into a register or count a counter up to a certain value. So reset and counter abstractions are very useful to short-circuit this process. It allows formal to control this element more directly. So these approaches help reduce the formal depth required to verify some interesting activities. Abstraction modeling is very useful for handling complex data elements inside design. So for example, in the networking and data transportation design, there's a lot of symbolic data elements inside design. So instead of representing the multi-dimensional arrays of data elements, we only need to represent a single dimensional abstract models. So it will certainly reduce the cone of inference and design space for formal verifications. So for example, in the RTL code, we may have a very complex system Verilog elements and a long array of it. So instead of representing this long array of system Verilog elements, we only need to represent one symbolic location. By keeping the symbolic location constant, we are writing and reading from that single locations only. Now, since this symbolic location is unconstrained, formal verification can explore the complete address space and exercising all the possible scenarios. So one very good examples are memories inside design. So instead of representing the two-dimensional memory structure inside design, we only need to represent one element of the memories. So by keeping the symbolic location constant, we are reading and writing from that single locations inside the memory. So FIFOs are very common design elements inside a design. However, a deep FIFO has a very negative impacts on the formal performance. So we want to define abstract models for the FIFOs. We do that by defining a symbolic depth. A symbolic depth is less than the actual depth of the FIFO. Using stable, we keep the symbolic depth stable throughout the formal run. Now, instead of using the actual depth to determine the rollover condition, we use the symbolic depth to determine the rollover conditions. So since the symbolic depth is unconstrained, formal equation will explore all the possible value for the symbolic depth. It will use a small value if possible. Now, by using this approach, we will hit the FIFO full conditions much sooner than before. That will allow for modification to verify what happens when the FIFO is full and overflow. Next, to verify data transportation logic, we use the Whooper coloring technique. It's a good approach as it doesn't require any data to be stored for data integrity checking. So in this technique, we color the input data so that the sequence of 0110 is sent. At the output side, we verify the same sequence is received. Now the rules for the Whooper sequence is captured in the two SVA property below. Rule number 1, if the first one is seen, the next one should be 1. Rule number 2, if two ones are seen, only 0 should be seen. We can use these two properties to constrain the input sequence and to verify the output data. So once set up, for modification, we find a way to break the sequence. However, if proven, it confirms that the data is being transported correctly, it's not corrupted, duplicated, reordered, or dropped. To summarize, abstraction modeling is very important. It reduces the complexity of the design. At the same time, it will reduce the latency required for formal modification to reach deep into the design. Now, during the formal implementation process, we look at each of the end-to-end checkers. We check whether formal is doing a good job verifying them. If not, we examine the cone of influence to determine where abstraction is needed. Now, we can use simple abstraction techniques such as cut point or reset. They are straightforward to apply and we can try them out easily. On the other hand, abstraction modeling requires more planning and skill. So we have covered all the major abstraction modeling approach, including symmetric data, memories, FIFOs, data independency using Whooper coloring. We have not covered tagging, but you can find more detail in the paper. Now we are ready to take a look at some test cases. Although some of these test cases has been presented in DVCon before, we want to summarize them here so that we can understand how this end-to-end checking methodology can be used for different type of design with different level of complexity. First, let's take a look at a parameterized multicast crossbar design. So in this A-by-A crossbar design, each client can send requests to one or more targets. And each target has an arbiter in place to determine which requests get forward based on different kind of priorities. Now, this is an example to demonstrate how abstraction modeling can be used. So if you are doing simulation, you probably have to write checkers for 64 pair of client target. However, in the formal test bench, we are leveraging symbolic variables to select a particular client and a particular target and implement all the checkers for that particular client target pair. Then for modification, we explore all possible values for the client target and to ensure that none of the checkers will fail. We partition the test bench into control path and data path. So for the control path of the test bench, we have multiple checkers. We have an arbitration checker to verify the arbitration scheme, a consistency checker to make sure the grant is given correctly, and a perform checker to make sure that operations are performed correctly when the condition is met. So for the data portion of the test bench, we have a data integrity checker. The data integrity checker makes sure that data is going from the input to the buffer and then from the buffer to the output port correctly to either ensure data is not corrupted, duplicated, reordered, or dropped. Now, since the data is not transformed, this is a perfect case to use the Whooper coloring scheme. It doesn't require any data storage. Now let's take a look at how we verify this design using end-to-end formal checking methodology. The design is not complex, so there's no need to partition it. So based on the specification, a good formal expert can identify the end-to-end functionality. They include data correlates, arbitration workload, sequence of data flow. Now for implementation, formal engineers implement a single formal test bench. It captures the two interfaces, the client input and output interface and the target input and output interface. The data correctness functionality is verified using the data integrity checker with the Woover coloring technique. The application priority is verified using the application checker at the target destination site. The sequence of data flow is verified using the forward progress checkers. As mentioned, to reduce the complexity, we use the symbolic variables to model the client target pair. Now, for formal closure, we validate the formal constraints in simulation. Now, during the formal process, we were able to catch 73 known RTL design issues in the design. So finally, for formal coverage, we were able to run all checkers and constraints on a good size server and achieve 100% line and condition coverage. The second design is a level 2 cache request coalescer unit in a GPU design. So there are 6 virtual channels that are processed in parallel, and the flow is credit-based, with credits issued by the L2 on a per VC basis. So the problem is in a design like this, the top-level simulation will never exercise the block sufficiently to verify the potential deadlocks inside design. So blocks with embedded store condition may introduce dependency and as a result deadlocks. So in this case, we developed a special end-to-end checker to detect circular dependency in the store conditions. So this circular dependency checker will exhaustively traverse all entries in the dependency table and detect all possible loops. So to reduce complexity, symbolic variables were used to enable formification to select the initial store block and process the rest. So this end-to-end checker has been implemented successfully to verify that this design is deadlock free, and also it can be used for future projects. Next, let us take a look at how we developed the end-to-end test bench in the 3 phases. So in the planning phases, since the design is complex and there are multiple blocks in the design, we took a divide and conquer approach. We implement different test bench for different submodules inside design. So in this case, there's a test bench for the request module, and there's a test bench for the respond module, and there's a test bench for the top levels. Then we prioritize the functionality of the design, all the functionalities, and all the IP blocks in the design, and then we implement specific checkers for each of them. And to reduce complexity, first of all, we black box one of the submodules, and the submodule will be verified independently. And for FIFOs and CAMs inside the design, we shrink the design size. And then we also partition the VC path to reduce the latency. Now to implement the end-to-end formal test bench for this design, we first start with the interfaces. There are 2 major interfaces in this design. One is the crossbar interface, another one is the L2 interfaces. We use protocol monitor to capture the interfaces at the same time constrain the input port. Now for end-to-end checker, there are multiple functionality we want to capture to make sure that they are correct. So first of all is the request coalescing, the data integrity, the response replay, and the forward progress checkers. Now, since the design has very long latency, we have to use multiple abstraction techniques, such as the counter abstractions and the Woover method for data consistency. And for modeling, we use the symbolic address for the CAM. So for formal closure, we have integrated all the protocol monitors into simulation to make sure that we have not over-constrained the design. At the same time, all the monitor has been cross-proofed among modules to make sure that they are consistent. So during the process, we have identified 57 bugs, and 7 of them has been recognized as corner case behavior that will never be found by simulation alone. Now, when we first start measuring formal coverage, we are not even close to 100%. But as we are developing more and more checkers, and also we make sure that we have checkers on every output port, so finally we were able to get 100% coverage on both line and conditions. So the final design is a network-on-a-chip configurable cache controller. Like many cache controller we have verified before, cache controller has many corner cases and has many configurations. Simulation alone is not able to deliver the level of confidence for productions. Now to verify this cache controller, and one of the decisions we have made earlier on to handle the design complexity is to create 2 separate test benches. So we have created one formal test bench for the tab type and another formal test bench for the data pipes. We maintain a very clean interface between them. We capture those interface properties, and then we cross-proof those properties to make sure that they are consistent. Now, also to handle the complexity of this design, we have used the abstract modeling to handle the memories inside the design. This configurable cache controller is a complex design. So we want to have a more expert involved earlier on in the design cycle. Now, as it turns out, the original estimation is over 1 year. So given the complexity and the schedule, it is wise to create 2 test benches, one for the pipe, one for the pipe, so that we can have 2 from one engineer working on in parallel. Now, the original design consists of typical design blocks, such as arbiters, cache-like controllers, DDI controllers, and files. Although they are used for abstraction, so these physical partitions are not exactly aligned with what we want to do. So SV statements are used extensively. They are used to map the tap pipe test bench to the design, the data test bench to the design, also a virtual interface between this test bench. Now, since we know earlier on where we require significant of CPU resources, so we have reserved some full machines so that we can run test benches, checkers, constraints, time. It turned out this is a decision because we power servers, we need to do as much abstractions needed. We can focus our effort on the ones. So for this scalable cache controller, we don't have to go through test bench different phases details. We find all the information in the paper. I want to focus on end-to-end check and the abstraction. Now for end checker tag pipe, we are using end-to-end check to verify the state machine address and also placement policy. For the data pipe, we end-to-end checker verify read the equity, so the eviction. Now the design is complex, so we are using a lot of abstraction tags that include that abstraction, cut point, as area, saying for the and data map. Now for consistency, for data consistency, we are using coloring. Before we conclude, we want to share a few useful experiences. Every task smoothly from right, but there will be exceptions. Now the most common is when the checker will deep in achieve the abandoned. Mentioned before, examine the inference, determine what action is needed, and apply them. However, while that, we can also include checkers to the environment. They can be provided in this regression. Case is coverage insufficient, so the case we have is to have every output. So based on this with the worst situation is either to go planning phase, post the function or the when differently. This is divide and control system. It is not risk and engineer them concur. Now, finally, either last at some company resource will realize the form very now if those are available, time clouds such as or price the alpha and
Hey, Aiden, can you hear me?
Comport and check and
Yes.
Yeah, I think we probably should just stop the video, and it's not very productive. Ping, maybe we just talk about the last few minutes. I think you have your slides. You can talk live.
Okay. Yes. Can you see my slides?
No, we're seeing your Yeah, we're seeing your desktop looks like the slide.
Okay. Let me try again.
It's like a live performance. I always have technology issues.
Okay, are you seeing my slide?
Yes.
Okay, very good. All right, so I think let's go through the last slides. Actually, I think that's probably the most feedbacks and complicated slides. And actually, after we have deployed the methodology, we noticed that there's definitely some iterations. So ideally, we want to see that everything is going from left to right perfectly. But actually, in a lot of cases, there are situations we need to go through iterations. So one of the very common situation is for some of the complex checkers, they may be not inconclusive. So for inconclusive checkers, there's two approaches. One, you can certainly promote them to simulation. Now, on the other hand, if the complex checker, you can also examine the cone of influence or the offending cone to see what is causing the problem over there. So after you have examined the offending cone, and if there are abstraction, you can perform abstractions. And also to simplify the cone of influence, you can definitely add cut points and constraints to drive the formal tool further. Now, formal coverage is another area that sometimes require iterations. When you examine the formal coverage, you may notice that part of your design is not covered. So one of the things we do very early in the design cycle to avoid the formal coverage problem is by adding, look at the assertion density is available from all the EDA vendor, and to make sure that the assertion density is good. And also another very important thing is adding assertion to the output port, because a lot of time you're verifying the state machine inside your design, but how about the fan out of the state machine to the output port? So we make sure that there's assertion on all the output port as well to make sure that the formal coverage is good. So these are the two major iterations we have to perform in most cases. Another thing which is I want to highlight is also the number the test bench. So for example, when you can decompose the design, the functionality of the design, and instead of, for example, you're verifying one RTL module, it doesn't mean you only need to have one formal test bench. You can have multiple formal test bench with different formal test bench to focusing on different part of the design. So as we mentioned earlier, we can have a test bench focusing on the data path, or a test bench focusing on the control path. Or you can have formal test bench focusing on special functionality in the design. So for example, recently, we have formal test bench focusing on the safety mechanisms inside design. So by having multiple formal test bench or multiple layer of formal test bench, you can do a divide and conquer approach and also allow your formal test bench to be much more reusable. So when you are doing the next generation of the design, you, instead of changing your complete formal test bench, you may only need to change one part of your formal test bench or replace one of the formal test bench. So that is useful. So finally, I think we just want to, the benefit is to reduce time to the first bug and then reduce time to the last bug. And I want to acknowledge the team in India helping a lot, and they contribute a lot of information to this presentation. So I think if there's any questions, I can take the questions.
All right, thank you, Ping. Yeah, that was very excellent talk. We can all learn a lot from this methodology. And let's see, as far as questions, I saw some of them there. One of them is, when you say checkers, these are assertions based on checkers and abstract models.
The checkers are basically RTL codes and SVA. So the checkers are actually on the abstract models, inside the abstract models.
Okay.
So maybe I go back to the
I'm looking for, and the next one is how does having multiple formal test benches relate to case splitting?
Oh, so that is, as I mentioned earlier, there's two ways to reduce complexity. One is having multiple test bench to focusing on different part of design. Case splitting is the complexity of the property you want to verify. If your property is complex, you can divide up the property into multiple properties.
Okay, thank you. And is it a good way to describe assertion as a design specification by designer?
Actually, that is came up a lot recently. One of the very important thing, one of the first difficulty you will encounter is when you read the document written by the designer, sometimes it's not obvious it's not obvious how to convert them into checkers. So this is the this is the problems. So actually, we are starting to work with designer very early in the design cycle, so that when they start writing down, when they start documenting their design intent, we try to educate them how to document them in a way that they can. Having markers and having labels is very useful, and also describing the behavior in a way that can be translated more naturally into checkers. So one thing a lot of time designers fail to do is designers are very good at capturing the positive behavior, but seldomly you find the negative behavior in the document. So we are doing that, doing the education.
Okay, the next one is, do you think DCR controller is a good candidate for formal
verification? DDR controller is a very good candidate, yes. Yeah, especially if he has an AXI interface and DDR interface, yeah, then you have two interface you can use.
Okay. I have a question. So what is the most challenging part in this methodology flow that you talked about?
The most challenging part is actually the end-to-end checker. The end-to-end, yeah.
Writing the checkers themselves?
Yeah, that's right. Yes, writing the checker, because to write the checker, you have to understand the design intent. Underneath the design intent is one of the, I mean, as we all know, the design document never capture everything. So you have to work with the designer very closely. So we definitely see a difference when we engage early with a design team, we get to talk to the design team, we get to involve in the design review, that helps a lot. When we engage late, when the RTL code is kind of like frozen, the designers forgot why he made that trade-off or why he made that decision. So engaging with the design team early definitely helps a lot.
Great, thank you. I think in the interest of time, let's wrap up the Q&A. Well, let's put our hands together to thank Ping. Thank you. And please don't forget to vote for the best paper. So now, thank you. So now it's the time for our next speaker. His name is Vikram Khosa. And Vikram is a principal engineer at ARM Austin Design Center. Since 2013, he has been driving formal verification efforts in Austin on the AI class CPUs and now driving ARM-wide formal initiatives. Before that, he led the memory system verification effort on the Cortex A15 CPU and other verification roles, including a couple of early stage startups. He has a bachelor's degree from BITS, Balani, and a master's degree in computer engineering from University of Minnesota in Twin Cities. He's here to tell us how to take scalable approach in formal. So please welcome Vikram.
We're going to present our paper on Hopscotch, a scalable flow graph-based approach to verify CPU store execution. And to start off with some background, we'll briefly touch upon the design and formal environment, talk about some complexity mitigation techniques that we've used in the past, introduce the ARM memory tagging extension, called MTE, and then the main case study being verification of store execution with MTE. We'll start off with verification requirements for MTE, then introduce the Hopscotch methodology, and follow up with a discussion on how we implemented the store execution checker based on Hopscotch, discuss some results, and finally conclude. So let's look at the load store unit first. This is the main design under test. This is by far the most complex unit in the CPU. This includes the L1D cache, and the area outlined in red contains all the units that constitute the store path, which is what is being covered by these checkers. And just a quick description of the flow. We start off with a micro op for, let's say, a store being issued, and it goes through address generation, gets checked for faults while being also looked up for its physical address and attributes, etc. And then eventually settles into a store address buffer for the address part, and a data buffer for the data part. And there's a separate side structure called the RST, which tracks fills, etc., at a cache on a cache line basis. And once the stores are non-speculative, they will merge into a merge buffer, which then will eventually write to cache. For any misses, we have a separate fill path that the RST manages. So as you can see, most of the design is covered in the store path, which we'll try to verify. This slide just shows a schematic of the test bench architecture. I won't go into detail here. More details can be found in the paper if you're interested. I will skip this in the interest of time. In terms of the kinds of strategies we use for complexity mitigation, use design mutations, abstractions, over constraint based state reduction, as well as structured case splitting. We have some slightly novel techniques based on a couple of these strategies that we've described in the paper as well. So now let's introduce the ARM memory tagging extension. The problem this is trying to solve is that there are memory unsafe languages such as C++ that allow unintended data corruption or unauthorized access to sensitive data. This typically manifests itself as a bounds overflow or a use after free type of issue. And the solution here is to support coloring of memory allocation, which is typically lower overhead and probabilistic, so it's not bulletproof. And the algorithm here is to assign a color to each memory allocation, store the color in some unused bits of the pointer. Every time you reference that piece of memory, you match the color to what's stored in memory. And every time you free the allocation, then we reassign the color. The key rules around this are in the architecture are that all loads and stores that are checked using this feature carry a logical address tag, and we've got 4 bits of physical address tag that are stored per 16-byte granular memory in cache or memory. And then the MTE itself can be enabled or disabled at different granularities by either by exception level or across page boundaries, etc. And for any checked accesses, the LAT, the logical address tag, is compared against the PATs for all the overlapping granules in memory. We also have separate instructions called LDGs and STGs that are used to read and write these PATs. In terms of how the tag checking actually occurs, there are 2 separate modes. One is known as the precise mode. This is a high performance overhead mode, typically used for testing software. Here we require the tag check to succeed before the store merges. And if it does fail, then also it will abort synchronously, allowing for that hop to be flushed. In imprecise mode, which is typically used in production mode and has lower performance overhead, the execution is not gated by tag check succeeding. So we still go on as usual, except we will signal an asynchronous abort. This slide just shows, just kind of indicates the overall verification complexity of this feature. I'm not going to go into a lot of detail, but this just to illustrate there's different variables and different corner cases that all intersect to create this this verification space. And so we decided to let's see, let's go ahead and try to write some new checkers for this. So we started planning. That pointed to multiple independent checkers, both architectural, microarchitectural, to verify the store path. And this had to be done across different tag check modes, attributes, instruction types, alignments, etc. So as we kind of divvied up this set of checkers, we realized there was going to be significant overlap and tracking required for all these checkers, as it was sort of divided, amongst a small team. And then that pointed to a lot of duplication of effort. So we asked ourselves the question: what if we developed a more unified framework that spanned the entire life cycle of the store micro and identify key events, both architectural, microarchitectural, and instead of creating a more conventional scoreboard type structure, instead we just specify legal or illegal event orderings between these events for each flow. And this could, the flows could vary by mode, precise mode, imprecise mode, instruction type, and other attributes, etc. And at each event occurrence, we could check to make sure that we arrived at that event safely, that everything else before it happened correctly, and also that once we reached there, that we would eventually make forward progress. And also at interesting points wherever tag checking happened, we would key off some checks, and also data and tag consistency checks. The potential advantages we saw were that this would be flexible, this could be iteratively built, it would be modular, and also scalable. And we'll talk about some of those in the coming slides. The key intuition behind Hopscotch is that a store execution flow can be viewed as a non-deterministic abstraction of all legal store executions, represented by a flow graph for a given flow type or attributes. For a given such flow, each event in the flow graph can be represented as a visit to an event node in the graph. And each directed edge on the flow graph captures a single type of relation. And each of the nodes can be of a different type and can have different attributes as well. We also define the notion of a rendezvous node, which is a subset of such event nodes grouped together with barrier semantics. And this is used to define some forward path requirements from nodes. And we'll see some of this as an example in the coming slides. This slide illustrates a more abstract type of flow graph. So as you can see here, we have different types of nodes that are connected to each other via different edges. The different colors here represent different types of relations. Let's look at a more concrete example. So we'll take a store exclusive, which is a type of conditional store in precise mode. And here, a legal hop is represented by a unidirectional blue arrow, and a legal hop is a red arrow, and a mutex relationship is represented by a bidirectional dotted line. So as an example, we can have a micro op that starts off being accepted. That's the time we enter this graph at the root. It can get allocated or linked to a store buffer, and right away it can fail an exclusive check. It can also initiate a tag lookup and fill, which could be aborted. And typically here we'll do a tag lookup if it was just allocated, and then it could either pass or fail the tag check itself, and eventually resolve clean, which indicates that it was it can go ahead and become non-speculative, or it can resolve with a fault. Once it's resolved clean, it will allocate or link to an existing merge buffer, and then the store buffer can merge into the merge buffer. At this point, it can also go through potentially another exclusive check, and it can again fail or pass the exclusive check, and eventually, and if it does pass, then it will get written to L1D. And once you have an exclusive check, or either fail or pass, it will be broadcast as a result. And now let's look at these, different, for example, the red arrows here indicate that these are legal hops. We can't have a pass tag check that will eventually resolve with a fault, or vice versa with a resolve clean that was preceded by a failed tag check. And for example, you can't have resolve clean and fault happen at the same time. And so that indicates a mutex condition. And on top of this, we can also define path inclusion or path exclusion conditions. For example, we can define a requirement that an L1D write always be preceded by a tag check passing or a resolve clean. Similarly, we can here infer that the pass exclusive check should always be preceded by a pass tag check, and so on. In other cases, an L1D can't be written to if we have failed either an exclusive check or a tag check, and so on. Okay, so let's briefly talk about the design goals behind Hopscotch, how we implemented it. So what we really wanted was a clean separation between a user-defined maintained layer of functional specification, which is able to express some simple ordering requirements for design events which are abstracted. And below that, we wanted a static, very concise set of code that operates on very regular structures that are configurable based on the user-defined layer, and is really domain agnostic, can be used for pretty much any kind of execution flows. And what this lower layer does is translates and stores and executes this user specification, and also allows us to generate automatically a whole set of checkers and coverage. The key requirement here is that this be easy to maintain. So this allow any kind of updates to the spec to be clearly captured and also tested interactively based on counterexamples. And any such changes should have little or no change to the underlying code base for the more regular code. And also another benefit would be ease of decomposition. So it should support automatic case splitting and also decomposing an entire path into smaller paths. And both of these are key to addressing formal complexity. This is what a sample node specification looks like. Again, we've chosen the exclusive check fail. As you can see, we've defined certain macros that capture each of these types of relationships between nodes. And we just simply define them here as declarations. And that's pretty much, that's the entire spec looks like this. How do we implement this in the larger test bench? So over here, we look at the filtered events from the DUT, which have been passed to an event monitor. We also track the state of the transaction, in this case being the store. And both of them feed into what we call an event notifier, which really takes these events, each event, or a set of events that are being reported each cycle, and feeds them into this trace graph structure. And the trace graph structure effectively contains the flow multigraph that represents the spec, and this is some additional state it will track on top of that, and essentially maintain this state of a given trace. And again, zooming out a bit further, and then we essentially attach our different checkers for flow safety, flow progress, and additional checkers that key off of some events on top of this. Now let's take a closer look at the various types of checkers that can be automatically generated from the flow graph specification in Hopscotch. So we'll start with safety checkers. These are the different types of safety checkers that are present. The trace state checker simply tracks the state of the entire trace and ensures that it never becomes illegal. And there are separate per node state checkers that also track the state of each node individually and base them on node type and trace state. These also include the notion of revisit bounds, where depending on the specification, we may declare the state of a node as legal or illegal based on how often it was revisited or revisited. The hop safety checkers simply look at each of n nodes currently visited and check them against m nodes visited last, and ensure that all m times n node hops are legal based on the specification. Similarly, concurrent safety checkers look at each of the n nodes visited this cycle and check that no concurrence relations are violated with respect to the remaining n-1 nodes. The path flow safety checkers are also invoked per node visited in the current cycle and check against all other nodes for any path inclusion or path exclusion relations being violated. Now, next, let's look at the flow progress checkers. And these are assumed guarantee based. So the progress checkers themselves come in two flavors, hop and rendezvous progress. And there's a separate set of checkers called stall clear guarantee, which essentially is the assumed guarantee part of it. So, for hop flow progress checkers, this is again invoked for any non-leaf nodes that are currently visited in this cycle. And as soon as we visit a given node, unless we escape or abort the graph, and depending on if we hit an escape node or a failure node, we always want to make sure that we will visit at least one node to which a hop is legally defined eventually. So there's the liveness variant of this. There's also a bounded safety variant where we're comparing, against a predefined threshold. And we have a smart counter, which only counts during cycles where there are no legally defined internal stalls. And this is where we're assuming them as bounded. We will assume that they will eventually clear, or external wait conditions are active, and that we haven't legally hopped to another node yet. Similar to this, we have the rendezvous flow progress checkers. We've already talked about what rendezvous nodes are, essentially composite nodes with barrier semantics, and starting at a visit to any node, which could also include a rendezvous node. Unless we escape or abort, we will always want to eventually visit all required rendezvous nodes downstream. And again, we have a similar definition for the bounded safety variant. The stall clear guarantee checkers are again invoked for any non-leaf atomic node which once visited. And again, this is coupled with progress checkers. Here, for any internal stalls we assume is bounded at a given node, we will independently guarantee they will eventually clear. So there's a liveness variant again, where we say eventually we will clear, assuming fairness on the external weight conditions. And there's a bounded safety variant where we say it should clear within a specified number of cycles depending on the microarchitecture. Let's discuss results briefly. So we hit around 19 bugs with this set of checkers, and roughly half of them were found by formal only, and the remaining were either reproductions or found in parallel with simulation. One thing to keep in mind is that this was pretty late in the project. 6 of these were found post-release. So we'll look at some sample bugs found by the flow safety checkers. So safety bug 1, it was a node state check. Again, what we're doing is each node is allowed to be visited only a specified number of times. That's part of its node attribute. Here, the bug was that the RTL was writing a tracked STG ops bat and dat at different times to cache. In fact, it was writing the same bat twice. And this was also hit by hop safety check. Another type of check that failed for in a different bug was a concurrence check. Here we're checking to see if node A is visited, then node B should also get visited in the same cycle. And here the bug was that RTL was writing a tracked spat without writing its stat. This is an example of a bug that was found by the flow progress checkers. Again, here, this is a rendezvous progress check. We're checking if node A is visited, then at least one hop-related node B, and all required downstream rendezvous node C from A should eventually always get visited. So in this bug, this was a precise mode store, and the RTL executes a tag check for, again, a store exclusive micro op. However, it fails, the tag check fails due to hitting a poisoned bat in the cache. However, since the exclusive monitor was unarmed, it signals that the store exclusive failed. However, it never arbitrates to broadcast the failure, the result was. Because the merge buffer was never written due to the tag check error that came in because of the poisoned bat. Here, progress checker fails because a required rendezvous hop from store exclusive failed to store exclusive result was never taken. And in fact, we hit a couple of variants in this bug. Some key observations based on our experience with Hopscotch. It helps us accelerate store execution bring up tremendously. The safety checkers were especially valuable for sanity testing, which it got lots of otherwise quite tricky test bench issues quite quickly. Our debug productivity also got a boost from visual logging of node visits, which helped us, kind of tell what's going on in a given trace at a glance. Performance of the matrix implementation of these graphs turned out to be quite sensitive to the total number of nodes, which added complexity, size, and memory requirements. So that's something we needed to be cognizant of. While deciding which nodes to add, we limited ourselves to high-level events at first, but then eventually progressively added additional microarchitecture events, which required to be modeled a little more precisely. So the trade-off here was checker precision versus the effort required for modeling. One other observation was that our liveness checkers didn't yield many results. This is possibly due to a different source of complexity that which we're still investigating. In conclusion, our vast investments in complexity reduction for the test bench had a significant impact on the baseline performance. We also learned as part of this experience and confirmed that focusing on the right problems with the right set of tools is critical to adding value. And all the time and effort we spend carefully planning both the scope and the implementation of this effort paid for itself. The Hopscotch framework in particular proved to be a rapid, flexible, and scalable way to both prototype and test our end-to-end checkers. At the end, we were able to develop a mature formal environment for the load store path within a couple of months, and we're able to add quite a bit of confidence to our release. Thank you for your time. I'm happy to take any questions now.
Thank you, Vikram. Thank you for this insightful presentation. We can all benefit from it. And let's see, please type in your questions for Vikram in the chat box, and then we'll take them. In the meantime, I have some questions for you, Vikram.
Sure.
So could you describe some of the other complexity reduction techniques used other than Hopscotch?
Right, I think I already had a slide on that, or I briefly talked about things like, I think most of those are fairly well-known techniques, design mutations. We do have a couple of, I guess, maybe a little novel twists to some of the over-constraint-based state reduction. We have developed some infrastructure around creating what we call transaction limiting profiles that allow us to manage sort of complexity of stimulus that we allow. That's one, and also case splitting, sort of more structured case splitting, as well as obviously abstraction models. We make quite heavy use of that.
So one question came in, says, could you give an estimated on time and effort spent in Hopscotch planning?
Yeah, that's a good question. So this was around, I would say around, so we went down the path of planning for this feature. I think it took us around a couple of weeks to come up with the set of checkers that we needed, and reviewed with designers, et cetera. But then, we kind of put our heads together and we decided maybe this is time for a different approach. And that once we had that idea, then I think it was maybe another, I would say another week or so before we kind of had an idea of how to go about it. In fact, even the implementation of the actual Hopscotch code was surprisingly fast. I think I had like a working prototype in like a week's time. It's very, very small. It's very small code base. The main effort was to then actually define the specification process. Okay. Hopefully that answers the question.
Okay. Yeah, that's great. And one last question, I think we have time to do. Could you describe in more detail how these flow graphs are implemented in System Verilog?
Right. So they're right. So these are basically implemented as sort of a set of matrices, either sort of single dimensional or 2D arrays in Verilog. Very regular structures, and then we've got these set of macros that help us essentially program these, initialize these. That's pretty much it. Yeah, I think that's okay. Those are so we've got the checkers themselves, or the coverage itself just iterates over these regular structures to generate the actual checker code.
Cool. All right. Thank you. Well, we need to wrap up this session, so let's put our hands together. Thank you. Thank you, Vikram. And please don't forget to vote for the best paper. So it's time for our next speaker. His name is Anshul Jain from Intel. And Anshul is a formal verification solutions architect at Intel. He's been actively applying formal verification, solving hardware challenges, and for more than a decade. So at Intel, he leads architectural formal verification solutions for complex control logic-based design, targeting Intel's leadership server CPU family. He is also trying to spread the formal knowledge to different design and verification teams across Intel. So prior to joining Intel, he was an engineering manager at Oski Technology, where he worked with Qualcomm, Samsung, Cisco, NVIDIA, Xilinx, just to name a few. And Amazon as well to verify their design with the formal verification. So please welcome Anshul.
Hello everyone. Good morning, good afternoon, and good evening. Aarti and I are honored to present our work on behalf of Kiran, Bindumadhava, Shiva, and Siva from Intel. In today's presentation, we would like to share the work we are doing to leverage FE in root-causing post-silicon bugs, evaluating workarounds through exhaustive list of scenarios to mitigate the risk, and provide high-confidence bug fix to avoid respins. In this presentation, we will outline the risks and challenges posed by a post-silicon functional bug to the product schedule. We will then offer our FE solution to this problem in form of a methodology that enables fast-paced debug of post-silicon failures, accurate root cause analysis, and robust bug fix validation to mitigate any further scale risks. We will also share a case study to showcase the effectiveness of a proposed methodology. We will close with a summary and transition to the Q&A. Though our industry is embracing formal verification across breadth of designs, majority of the designs are still dependent on traditional dynamic simulation for functional sign-off of increasingly feature-rich and complex design. With aggressively shrinking time to market schedules, some inconsistencies still fall through the cracks and make their way into the silicon due to inexhaustive coverage in DV, resulting in post-silicon bugs. Formal verification is extremely effective in plugging such gaps. However, its application is limited due to factors like lack of expertise, design complexity, etc. Having said that, hitting a bug in silicon is extremely critical for product schedules. There's a lot at stake. In fact, with each passing week, stakes go higher. Therefore, an absolute assurance of root cause analysis and bug fix is required before a respin. Since Formal is good at finding needles in the haystack, it plays an important role in finding the exact root cause to provide the right sort of information to designers and microarchitects to help them come up with a sound fix. Not only that, since formal verification is a proof-based technology, it provides highest level of confidence and assurance about the robustness of a fix. There has been much skepticism about applying formal verification in post-silicon phase. It seems to be a challenging task, and I would agree. But let us get some myths out of our way before we address how to overcome the challenges of applying formal verification in post-silicon phase. It is a fact that post-silicon bugs are isolated on huge block boundaries, therefore the myth that FE will not be manageable at such big design blocks. It is also a fact that FE is usually not run on such large boundaries during pre-silicon verification. Therefore, stable environment is not readily available for reuse. Therefore, the myth that it will take unreasonably long to bring up the FE environment from the scratch. And last but not the least, not all the signals can be probed during post-silicon phase in verification. Only a general high-level behavior leading to the failure is observed or available. However, FE needs intricate signal-level details for the bug reproduction. We believe that these myths should not limit the application of FE, a methodology that has changed the landscape of pre-silicon verification drastically, on a verification stage that is final quality filter before the product is released to the customer. However challenging, we believe that inclusion of FE in post-silicon debug is crucial and can shorten the debug cycles and thereby time to market while having 100% confidence on the quality of the fix if applied with an intelligent approach. Through all these years, we have come up with a methodology, we call it Unearth, with stellar track record in applying formal verification effectively and accurately in post-silicon phase for success. It is a 7-step process that we follow to quickly build formal verification environment capable of root causing these bugs and evaluating the effectiveness of the workarounds and the bug fixes. We start with understanding the problem and collecting all the collateral that is available and try to find out what property or what formal property would have caught this bug. We then go ahead in etching the boundary, the design boundary on which we want to run the formal search, and also assess the reachability of the source of bug using some cover waveforms. During this process, we regulate constraints to strike a balance between over constraints and under constraints, and also tap the details that are available in the simulation waves to start a formal search from a warm state. We then harness the full potential of the formal technology to sign off on the bug fix. As a first step, we collect all the essential information and the details from the post-silicon design issues. Such details are instrumental in getting a head start in the right direction. These details will also be helpful during each step of the execution in the overall quest of finding the root cause of the post-silicon design issue. Each post-silicon issue comes with its own panic and paranoia, hence it is common to have multiple descriptions of the issue from various stakeholders, both design and verification side. We recommend to document all such descriptions and extract vital information such as effect of the failure. Was it a data corruption? Was it a deadlock? The sequence of events at different interfaces of the design. For example, did we see a dependent read request on an address on which a partial write request was already in progress? Or did we see a CRC error detection on a retry message causing multiple iterations, etc. Then we collect relevant specification and implementation document to understand the microarchitectural details of the design, such as primary and auxiliary interfaces, mode of operation, flow of transactions, etc. Such documents help climb the steep learning curve through block diagrams, reduce dependency among the stakeholders, and provide fresh perspective to the details. Source the design files from the version of the repository which made it to the silicon. It is a common pitfall to start reproducing the post-silicon issue using design files not available at the top of the trunk. Assess the information dump from the post-silicon test failure, such as the values of the configuration registers, error logging registers, or other debug hooks. Sometimes a particular manifestation of the post-silicon issue might be reproduced in dynamic simulation while formal verification environment is still in works. The simulation waveform will help visualizing the issue better. Finding a bug manifestation in simulation should not call off the formal verification effort because there could be more such scenarios which has not been found in the simulation yet. Though the design documentation would generally include timing diagrams, however, sample simulation waveform from directed test proved to be helpful while debugging failures seen in the formal environment. Sample waveforms can be used to brainstorm some over constraints and bypass formal complexity as well. Locate all the existing formal verification collateral available. It could be a basic environment to bring up design files in formal tool, an assertion-based VIP for standard interfaces, or even a full-fledged formal sign-off environment. Once the manifestation and the scenario of the failure are well understood, shift the focus to thinking about the properties of the design that would have been violated in the post-silicon failure. Start from the process by brainstorming general properties such as each request from the host should be eventually acknowledged by the device, or the device should send the response in the same order as requests were received from the host. And then move to the most specific properties such as buffer should always have one entry available for pointer management, or the dispatcher should not attempt to preempt the request more than n number of times, etc. Depending on the type of the failure and the level of the details we have gathered so far, we can come up with multiple such properties that are worth checking. Write all such properties in plain, simple, human-readable language without worrying about the implementation details for now. Once we have succinct definition of any property, we can engage with the microarchitects to identify the observation points of the property and implement it using a lightweight instrumentation code and SVA. Post-silicon issues are mostly isolated at subsystem boundaries such as memory controller, physical layer, L2 cache, etc. Bringing up even a basic formal property verification environment at such subsystem level would typically need a lot of effort and many complexity resolution techniques. Therefore, we need a better approach in selecting the design under test for locating the source of the bug than selecting the entire subsystem as our duty. Apart from general recommendation of selecting a design scope with minimal area for minimizing the complexity, minimal parameter for minimizing the constraint modeling, and standard interfaces so that we can use some assertion-based VIPs already available, we recommend picking a block boundary at which we have all the interface signals to observe the validity of the property brainstormed in the previous step. Assuming we have identified correct properties, this approach would yield counterexample under 3 categories shown in the figure. Feedback from the counterexamples would guide us in selecting or expanding our design scope to root cause the post-silicon issue. Starting with a smaller design scope is safe against false proofs and manageable as we increase the design scope by integrating the neighboring blocks in the duty without remodeling the whole environment. Most of the post-silicon issues are extremely corner case that require some highly unlikely sequence of events happening in a specific order and proximity. Though formal technology is highly effective in finding such corner cases because of its breadth-first, exhaustive search of the state space, these corner cases could be hard to reach due to the formal complexity. Depending on the size, the number of gates, flops, etc. of the property, we often run into situations where the formal tool gives up before reaching the states where the design would have failed the property. We call it bad state. Such bad states could be deep in the state transition graph. One of the most effective ways to guide bug hunting formal engines to reach such deep design state is to implement spot covers for the intermediate events for the manifestation of the post-silicon issue, and functional covers to witness the exact sequence of events that drove the design into the bad state. We recommend using simple FSM to model the sequence of events instead of complex SVAs. Another class of effective functional covers are the ones that generate witness to a particular warm state of the design at the time of the failure. For example, an exact state of the linked list with its head pointer, tail pointer, and node links, or an exact combination of the multiple state machines. Covers not only helps the formal engines to work more effectively, but they also help build confidence in the direction of our efforts and provide an estimate of depth at which the failure should be found. Suppose we know that the bug manifests mostly when an internal FSM transitions to a certain state, for example, say stomped or drain, after a linked list has been populated with a certain number of entries, say 10. Such covers enable the tool to use SAT-based constraint random engines to generate witness traces for deep states quickly and reposition the locus of bug hunting bounded model checking engines from reset state to the warm states. Keeping the formal environment under constraint is recommended approach to reach pre-silicon verification sign-off. However, both over constraints and under constraints play an important role in post-silicon formal verification effort. Since we would be running only a small set of properties to root cause the post-silicon issue, we do not need accurately constrained interfaces of the design. For example, if we suspect the design to be sending messages out of order, then we may not need to perfectly constrain the initialization interface, as the formal tool may figure out the correct initialization sequence to bring the design into a state where it can accept the message and send them to the output in out of order. On the other hand, we can narrow down the formal search by constraining the configuration registers to values observed in the failing simulation silicon test. This technique can be improved by carefully scaling down some of the configuration registers values to bring deep states closer to the reset state. For example, reducing the preemption threshold value to trigger preemption more often, or block some entries in the linked list to reach the full state with lesser transaction. Formal search can be made more directed by disabling traffic on interfaces that is not expected to participate in the post-silicon issue. We recommend the constraint strategy explained in the flowchart to reap the best benefits of both under constraints and over constraint for a faster reproduction of the post-silicon issue. Over constraint will help narrow the scope of the formal search and allow the tool to spend focused effort on failing scenario, and under constraints will eliminate the chances of accidental masking of real design issues due to lack of stimulus. Bring up the DUT without any constraint, set up the clocks and resets, and witness the logic is alive by running some basic sanity covers on the output of interest. Then over-constrain non-participating interface such as CAN, train, auxiliary channels, etc., and ensure the design is still able to toggle the outputs of interest. Switch back to under-constrained approach of adding or refining the constraint based on counterexample produced by the formal engines for the target property. Some of the large designs may require long and specific sequences of standard events before it could process the functional traffic. Common examples of such sequences are cold boot sequence, warm reset sequence, credit initialization, frequency sinks, etc. In pre-silicon, reset abstraction proved to be helpful in abstracting out such time-consuming, uninteresting sequences to start from the design state that can consume the functional traffic. However, reset abstraction may require certain refinement and can become an iterative process spanning over days and weeks of effort. In post-silicon phase, it is better to bypass long standard sequences more deterministically than reset abstractions. Simulation waves can serve an excellent starting point for the formal search from a warm state. All we need to do is generate a simulation wave, identify the timestamp where the design comes to a stable state where all the boot sequence, initialization sequence, all is done, and load the simulation wave in the formal tool and specify the timestamp of interest and start the formal proofs. While all these steps provide a fast path to root causing the post-silicon issue, they should be executed with a greater goal in mind. After root causing the post-silicon issue, same environment should be enhanced to evaluate the workarounds, verify the bug fixes, and achieve the formal sign-off. After successful reproduction of post-silicon issues and all its possible manifestation, it is strongly advisable to employ bug hunting, abstraction models, proof acceleration techniques to explore more bugs in the neighboring logic. Formal verification environment developed in post-silicon phase for the current version of your IP or SoC should be the collateral to verify other features or updates in the future versions of the IPs and SoC. With that, I would like to hand it over to Aarti to take us through the case study of post-silicon bug found in Scheduler. Over to you, Aarti.
In one of our SoCs, we were seeing a post-silicon bug, and after initial analysis, the bug seemed to be coming through this scheduler block. This block had three major interfaces, interface X, Y, and Z. Any packet that was coming through interface X in this block would go through a packet parser, where some predefined transformations will happen, and then the transformed packet will go through some queues and control logic and get routed to either interface Y or Z. This routing was determined by the resource availability of the modules connected on interface Y and Z, and also on some rules in the control logic. These rules were also dependent on the configuration register settings. The main challenge of formal verification of this design was its design size. It was a huge design size of around 4 million gates. To give you all an idea of what the bug was, there's a representative waveform on the slide where we see that on input interface X, there are 5 transactions coming, transaction A to E. And let's suppose based on the internal rules in the control logic, the transaction A is directed to interface Y and the transaction B is routed to interface Z. And next what we see is that transaction D is reaching interface Y, and after a while it is again seen on interface Y. So what we saw here was that transaction C is lost. What was actually happening in the design was that transaction C was getting scheduled on interface Y, but its parameters were then overwritten by the new transaction in the pipeline, that was transaction D. So this was the bug that we started chasing in the formal verification. In FP, we adopted the unearth approach, and as a first step, we studied a lot of simulation traces and the architectural specifications. And based on that understanding, we created a basic flow diagram of the routing which was happening within the block. On the right hand side, we see the flow chart that we created, and we see there are 3 endpoints. Any transaction that is coming to interface X can be routed to interface Y or Z based on a lot of decisions that were happening within the design. In the interest of the time, I will not go through the entire flow chart, but I would like to bring your attention to this temporal loop within this flow chart, where based on some decisions, a transaction can get replayed within the pipeline, while another new transaction can be coming at the same time and can lead to some conflicts. And this was the root cause of the issue that we were seeing in the design. After understanding the problem, we brainstormed on the list of properties or checkers that can help us verify this block. As a first step, we labeled some relevant events which were critical to this routing flow, and as we can see in this flowchart, we labeled some temporal events from 1 to 6. And then we thought that to prove the routing mechanism, we can prove the transactional order equivalence between a set of events. For example, any transaction that is reaching event 2 should be coming in the same order as it was received at event 1. Similarly, any transaction that is reaching event 3 should be coming in the same order as it was received in 2. And so on. We got a list of four properties where we can check the transaction order, checking between events 1 and 2, 2 and 3, 4 and 6, and 5 and 6. Then on further analysis of the nature of the bug that we were chasing, we thought that the first property, that is the transactional order checking between events 1 and 2, should be good enough for us to reach the failure. So we concentrated first on that property and deprioritized the checking of the rest of the properties. All these transactional order checking properties we wrote by using the formal scoreboards. Now that we know what to check, we concentrated on how to check, and as a first step, we thought of reducing the design scope. We knew that it is a big design of around 4 million gates and it will pose challenges to the formal verification tools. So we tried to reduce the scope, and also we understood that the bug lies in the routing logic, and so we can do away with the packet passing logic and the configuration register setting logic. So here we limited the duty scope to this red rectangle seen on the slide, and it led to a smaller size DUT, which was around 1.5 million gates, much smaller than our initial design, which was around 4 million gates. We did had some disadvantages with this approach, that we now had to model the constraints or the assumptions needed for the formal verification environment on the internal interfaces of the design, which were non-standard. But when we weighed the pros and cons, we saw that the advantages of this approach are much more, and we went ahead with this approach. After getting the list of assertions that are needed to verify our block, we added a lot of covers in our formal verification environment to check the sanity of the environment, whether we are able to reach the meaningful states, can we get to the valid states or not. As a first step, we added some reachability covers for all the relevant events we had determined previously. And then next, we tried to add a cover to get to the failure itself through the covers. So we added a reachability for a state where a previous transaction is getting replayed in the pipeline, and at the same time a new transaction is coming. And actually we got to see the manifestation of the bug through this cover. After having the list of covers and assertions that are needed to verify our design, we had to help the tool to reach those meaningful states by adding some under constraints and over constraints. For example, we added some reset abstractions on the critical resource counters so that the tool can play with those values and reach the counter cases faster. Also, we added some over constraints, like we fixed the configuration register values. Mostly we matched them to the values seen in the post-silicon simulation dump. Also, we reduced the number of physical channels. The transition that reaches interface X in the DUT can actually come through multiple physical channels, but we allowed it to come only on 2 physical channels to reduce the complexity. Also, we extracted some details from the simulation waveforms to expedite our formal search. For example, we loaded a valid reset state from a simulation state initially, and then once our environment was stable, we removed this dependency and allowed a broader reset state by doing this reset modeling. After we were able to reproduce our bug, we harnessed the full potential of formal technology by adding more properties for full functionality check of DUT and relax some over constraints, like we allowed more configuration values to check the DUT under more configurations. What we saw in this case study was that the post-silicon bug that we were trying to find was reproduced in just 4 weeks. And apart from this bug, we were able to see 4 other manifestations of the bug scenario in the design. The FV work helped in determining a robust fix, and we verified 2 fixes for the design and compared them functionality-wise and performance-wise. The FV environment that was made for this post-silicon debug was reused in the next project as proactive FV, thus strengthening the weaker link. And the key takeaway that we take from this case study is that design size is not a limiting factor in post-silicon FV. This was a huge design of 4 million gates, but by adopting the unearth approach and going in a planned manner, we saw that it was a doable task. To summarize what we presented today, we presented the Unearth approach, which we consider as a comprehensive guide for post-silicon FE. We saw impactful results in the 2 case studies that we shared today. And apart from these 2 case studies, we have applied this methodology in several other areas and we saw similar results. We also saw that simple checks can find deep issues in complex designs. We saw that in the 2 case studies we shared, we wrote the checkers on basic nature of the design, and that was able to catch some deep-rooted issues in the design. Also, post-silicon FE is very important as it helps us identify more design candidates for FE sign-off, which we wouldn't have considered as FE-friendly designs earlier. So it helps us to target more bug-prone designs for next generations. Thus, it helps us to transition from reactive to proactive approach and makes us catch some bugs early on. That's why we recommend that all post-silicon issues in control logic should be reproduced through FE. Thank you for listening, and now we are open for questions.
Right, thank you. Thank you both Anshu and Aarti. So any questions? Please type in the chat box. I have one question. So to what extent is Unearth methodology automated, and what are the manual steps you can carry out to implement this methodology?
Hey, Shaolin. I think currently the methodology uses some of the flows which are available in the EDA, leading EDA tools already. For example, loading the simulation waveform for a particular value of registers, or getting some automatic assertions and covers generated from that. But primarily this methodology is still manual, in the sense you have a lot of brainstorming to do, a lot of custom properties and assumptions to write. However, we do envision to improve upon the process we explained today, so that it can be automated to an extent where we are shrinking the time to reproduce the failure through formal. So we have seen so far, we have seen cases where we've been able to reproduce the failure or conduct these steps in few days to few weeks, right? And we want to make sure that we target the few weeks and shrink that to shrink that to a smaller number with more automation built into these steps.
Okay, all right, thank you. And there's a question from Eric. He says, when you say size is not a factor, is that really true in general, or did you just get lucky and able to localize to a smaller block in this case?
I think with all due respect, but getting lucky is something which is very hard to be, in a place when you're doing formal. But the thought process behind it is that if a bug was escaped through IP level simulation, SoC level validation, emulation, etc., you just have one alternative left to you, which is formal, right? And the way we attack the problem is that instead of getting lucky, we try to find out ways to define the boundary of the RTL, which is good enough, so that we are not working on a big, subsystem, or working on a lot of CAI, a big, huge CAI, but try to take the intelligent decisions where what to abstract, what not to abstract, what are the points where you can monitor a particular problem, and so on. So that is the reason why we say we don't look at the size, we look at the problem. Formal is the only way to escape, to help here.
Cool. All right. Thank you. So it looks like there is no more questions on the chat. So in the interest of time, let's wrap up the Q&A, put our hands together, and thank you, Anshu and Aarti. Please vote for the best paper. So now let me introduce the last speaker. His name is Scott Peverell, and he's from Intel. Scott received his degree in EE from University of British Columbia and joined Intel as an ASIC verification engineer in 2019. At Intel, he was focused on formal verification and methodology improvement, working on topics such as formal reuse and complexity reductions. And very good topics. So in his spare time, he enjoys hiking in the mountains of British Columbia and playing music. So please welcome Scott.
Hello, everyone. Welcome to our presentation on maximizing formal ROI through accelerated IP verification sign-off. My name is Scott Peverell, and I'm representing a team all at Intel, specifically Intel's Vancouver site, that created this paper and presentation. All right, so let's talk about a basic industry trend. So within ASIC verification, there's been a major increase in the use of formal verification over the last decade. Just looking at one survey that was done, we can see that from 2012 to 2020, we saw an increase from about 25% of environments using formal property checking, at least somewhere, to more than 40%. And we see similar kinds of increases in automatic formal verification. Many people have recognized the power and usefulness of formal verification, and our team certainly agrees. So formal verification can be very powerful, but there can be very limited ROI if you're not able to deploy it widely. And there is a lot of hesitation, though, among managers as well as some lay engineers about using formal more within your verification planning. And the reasons for some of these hesitations are the fact that formal can struggle with certain kinds of environments. So for example, large designs, specifically in terms of having a large gate and flop count, designs with high sequential depth, and also if your team simply lacks the sort of engineering expertise with formal to deal with complexity issues that can arise, that can cause people to decide not to use formal, even if they do recognize that it can be useful. So for formal to really reach its full potential, we need to be able to address these issues. Of course, there are a variety of complexity handling techniques, various abstractions and so on that others have documented in a variety of other papers. We won't be dwelling too much on that in this presentation, but we did apply some of them in our work here. A major focus is having good partitioning and planning, and we will discuss that more at length. Being very careful about where you're going to use formal and deciding that early on is important. And also making sure to get good formal reuse, which we'll also talk about extensively. That can significantly reduce the amount of code duplication that you ultimately have to do. All right, so what we are proposing fundamentally is a hybrid IP verification strategy. So our old verification strategy from projects in the past was focused pretty much almost exclusively on simulation. And we would have simulation reuse, we would do simulation at the unit level, and we would sign off there, and we could take some of that simulation collateral and reuse it at the cluster and IP, and even the chip level. This was generally based on like the UVM framework. But what we're proposing now is to ideally push as much verification to formal as is practical. So we're going to be mostly using formal at the unit level, but there will also be some use of formal at cluster level. But we'll continue to still use simulation in a few cases where it is strong relative to formal. So why would we adopt this hybrid strategy? Well, for one thing, we want to try and shift left and pull in the schedule as much as possible. And one major advantage of formal is that it is often able to find bugs earlier than simulation. We have some results later that speak to this. And it actually often handles small unit level designs better than verification does. And this is typically where verification starts. So you can definitely start performing verification earlier in the overall project lifecycle. And so as this diagram indicates, we're going to mostly be using formal at block, use potentially a mixture of the two at the cluster level. And then as we get more to the full IP or even the chip level, we will be using pretty much exclusively simulation or other methods like emulation. So just to give a brief overview of our project lifecycle, of course, we have the very first phase where there's early scoping and planning going on, the creation of the key microarchitectural documents that describe the IP and the chip. And at this point, verification is just doing some planning, but the planning stage is very important, and we'll talk about more later. Then as we get past the design kickoff stage, RTL implementation starts in earnest. Verification at this point would normally just be mostly concerned with starting to create the verification collateral that we use later. As you kind of get past the IM1 milestone, you would start actually doing bring up now that RTL is mostly ready. And then as you get past this IM2 milestone, you do more exploration, try and find hard bugs and other sorts of things. Also do coverage closure. And that would then continue and you finally progress to sign off as you get past tape in and then before tape out. Okay. Now, what we're trying to achieve here with this formal shift left is to try and find a lot more bugs during those earlier phases of the schedule. So in our traditional approach, which was centered around simulation, we normally observed a bug graph that looked somewhat like the orange line. Very few issues were found before the IM1 milestone when mostly RTL was being coded. It started to really pick up after IM1, but probably more than half of the bugs were not found until after this IM2. A lot of issues were still being found as we approached tape in, and sometimes even after. But with this new approach where we're using a lot more formal and trying to do a lot more of it in parallel with RTL development, we can find a substantial number of issues before the IM1 milestone, find most of the issues before the IM2 milestone, and it only remains to find a few difficult bugs through bug hunting techniques as we move towards tape-in. And there's a big advantage in finding these issues earlier because there's typically substantially less impact. The earlier a designer goes and fixes an issue, they don't potentially have to change many other aspects of the design in order to accommodate what may be the new design behavior after the fix. Okay, so just to reiterate, we are proposing a hybrid methodology. We're not saying just do formal. We still think simulation has value in certain cases. We think that it's primarily still useful at the cluster and IP level, cases where inherently the gate and flop count is very large. And also when you have very long sequences that need to be verified, things like MediaFi training and link up, doing bandwidth measurements over many operations, power state transitions, doing a co-simulation with firmware. These sorts of things is where simulation is still generally the better approach. So in our kind of comprehensive sign-off methodology, we can think of it as being 5 key stages of verification. So the first is the planning stage that we do working with the microarchitects. We have a sort of initial setup stage where we start to create the basic formal collateral and the test bench. We have then the RTL coding and bring up stage. And in this stage, we really are trying to do in parallel, the designers are starting to create the RTL and we immediately try and bring it up in our environment that we've already started to code in the previous stage. And then as we exit that and we verified all the basic functionality, we can go and we can do formal exploration and code coverage as we then move towards sign off. Okay, so talking more about planning, it is really important at the planning stage to choose carefully where formal verification is going to be applied as opposed to doing some other technique like simulation. It's also very important to think about precisely what are your actual units for verification. Do you combine 2 things together for verification? Do you verify them separately? Maybe then have a reuse environment where you verify the 2 or more acting in concert, etc. And you want to be thinking carefully about this stage about the potential for FV reuse. And that can be both reusing formal verification collateral in another formal environment and also reusing it in a simulation environment. And we'll have examples of both. Okay, so just as an example, here we had here we have basically a simplified block diagram from an IP where we applied this. We have a variety of unit level environments. Those are the various boxes that are blue or yellow where we did verification. And you can see for the majority of the ones in the subsystem, the verification was done all informal. Those are the ones in blue. For a couple blocks, we chose to still do things in simulation. Those were ones where they were essentially like memory wrappers. We thought that that was still a case where simulation made a lot more sense due to the operation of the block being heavily centered around this memory that couldn't really be abstracted. And then we also had a block where we actually did a mixture of formal and simulation. And then we also went and we had a cluster level environment that's indicated by the blue dashed line, where we took several formal environments and we stitched them together and we did formal verification again with some end-to-end checkers, and we proved some more properties. And then finally, there was one big simulation environment on the whole IP where we integrated all of the individual parts and tested some end-to-end behaviors. Okay, so another key part of our methodology is doing this RTL coding and FP ring up in parallel. And this is kind of inspired by a test-driven development concept. So we have the verifiers working very closely with the designers to figure out what sort of features will be prioritized for implementation. And then those can also be prioritized for the implementation of the related constraints, checkers, and coverage that would be needed. And working closely with them, we were able to almost immediately start running checks, approving assertions and collecting coverage on an RTL feature immediately after it was coded. And in many cases, actually finding bugs very quickly and reporting them back to a designer. And then this process can iterate as you go through the various features of the design. Rather than typically in our old simulation-based methodology, mostly the design was completely coded before verification really started. During this time, generally in simulation, a lot of verification simulation collateral had to be created, and only then it was kind of started on the complete design. And we have designers really being kind of co-owners of the bring up task and working very closely with the formal engineers here. And then after we get past this stage, of course, we have formal exploration and sign off. I won't talk too much about this, but the basic concept is that to do formal sign off, we want to have 100% functional coverage hit. We want to see no failing checkers, of course, and we want to see that of all of the assertions that we have, that they're either fully proven or that they're at least bounded proven, and their bounds are greater than the related coverage bounds. And besides just doing FPV, we can also leverage a variety of other formal apps for the purposes of sign-off. We use, for example, SEC for dynamic plot gate equivalency checks. We use the CSR app for checking some access policies to our registers. We do connectivity checks. We use the CDC app when we have CDC crossings. That includes FPV with metastability injection. There was a paper just published late last year in Jug that was actually heavily focused on this FPV with metastability injection concept, if you're interested. And so this just visually kind of shows the various scope of the apps that we're using. SAC, CSR, FPV, connectivity, XProp, CDC, all working together to do formal sign-off. Okay, so as I mentioned, formal reuse is another important part of our methodology, and we can practice reuse in a variety of ways. We can do reuse of formal in another formal environment. We can do reuse of formal in simulation. We can do another mode, which we kind of call architectural FPV. And in the way that we basically enable reuse in these various modes is we have this basic concept of an FVC, formal verification component. And it's basically our reusable part of the unit level formal verification environment. So it would have end-to-end assumptions, some checkers associated knowledge logic, some covers that are all collected together. And the entire FVC has a mode parameter. And the mode is switched depending on how the FVC is being used. So when we're doing block level formal verification, the FVC is what we call an active mode, where we leave the checkers as assertions, we leave the end-to-end constraints as assumptions, and so on, as you would expect. Then when we want to do a reuse of that formal verification environment in simulation. Like let's say you had block A, it was formally verified. Block A is part of a larger cluster B. That cluster has a simulation verification environment. And you want to reuse some of the checkers and constraints you had from A's verification environment. You can go and you can take your FEC for block A and you can set its mode to what we call passive mode. And what that has done is it's converted the assumptions that we had within that environment into assertions. It's indicated by the green color. And the purpose of that is we can now actually check and see if the assumptions that we had at the block level still hold, and we can validate our constraints. That's very important to check that we're not accidentally over-constraining our formal environment. All right, and another technique that we can do is architectural FPV. I won't go too much into the architectural FPV concept. Other people have presented on it in more detail. There was a paper in DVCon 2018 that was all about the topic. But at a basic level, you're doing FPV where instead of having the actual design RTL, you have each of the individual blocks essentially represented with abstraction models. And you just have basically everything modeled with constraints, all of the interactions, and then you can have some end-to-end checkers. And you can check hard end-to-end behavior on this abstracted environment like deadlock checks. And the way that we achieve that with our kind of FPC methodology is we can take these FPCs, we can put them in what we call the architectural FPV mode, and that will basically convert their assertions now into assumptions so that their actual modeling logic now becomes like the abstracted model. What was previously checking the design's behavior now models the design's behavior for architectural explorations. Okay, so what are some of the results that we were able to get out of this whole exercise? So we were able to get some very good results on the shift left front. Here we have on this, this bug graph, the benchmark IP was from a previous project where we had done the simulation focused methodology. And as you can see, very few bugs were found by that first major IM1 milestone. But now when we're doing this new methodology, as indicated with the orange line, we were able to start finding a significant amount of bugs in the very first weeks. And by the time we got to the IM1 milestone, we'd already found 200 odd bugs, which is just based off of this graph around an order of magnitude more than the benchmark IP. So that really shows how much faster we were able to find issues. And just to give one specific example, we actually had a block where there was a deadlock issue, and it was actually detected on the very same day the RTL for it was coded. We just took the RTL that had been coded. We already had the related checkers already implemented in the formal verif environment. We just ran them. We found a fairly quick counterexample, reported it back to the designer. They were able to confirm it was a bug. And then we were able to implement the fix and verify that the fix worked. And this whole process only took like a couple days. So while that sort of issue would have probably been found in simulation, it would have typically taken, based off of our results from previous projects, much, much longer. All right, we were also able to get some good results in terms of quality. Especially trying to find kind of super bugs that are otherwise difficult to find. They're quite complex. Architectural FPV can help a lot with this. And we think there's the highest ROI when you do architectural FPV early in the process. We did have one case where we were able to prove the absence of deadlock on a whole subsystem that's shown here. It's essentially the same as the one from the previous example. So even though this design was fairly large, the actual RTL implementation, everything shown here was several 100,000 flops. We were able to reduce the flop count with the architectural model, just with the FVCs in their Arc FPV mode. We were able to reduce the flop count by more than an order of magnitude. And so our end-to-end checkers were actually able to get some good results, which would have been very unlikely to converge if it had been done with the actual RTL, and it would have been probably tough to discover the same kind of issue just through running simulations on the same cluster. All right, we're also able to get some good quality results in finding some issues with interactions with third-party IP. This has been an issue for us several times in the past on past projects. And we were actually able to find an example of this very early. Basically, what had happened was there was some misunderstanding about essentially the interface protocol or the interface behavior with a certain piece of third-party RTL. And our designs were actually being coded towards that incorrect understanding. And our checkers had been essentially based around that same misunderstanding. And we were able to just basically have an environment where we had the third-party RTL that had been delivered from the vendor, and we combined it with just our protocol checkers, and we saw basically like a violation of our protocol assertions. And we were able to then actually root cause that it was due to our incorrect specification, which was ultimately driven by a misunderstanding of their intended behavior. So these sort of things can be really tough to find. You might not find them until much later in the process, especially if this interface in your, say, simulation environment isn't at the boundary, but we were able to find it very quickly with our methodology. We're also able to get some results just in terms of our team growth. You know, having more formal expertise on the team is really important to getting more formal adoption. We're able to get a lot of our team members to do formal for the first time. The majority of our engineers on this IP were actually doing FV at some point, which was very much not the case for previous projects. And we also got some good learnings in terms of how to better do formal reuse and architectural FPV. So briefly to summarize, what we want to get at our future work is we think that there's definitely value in trying to drive reuse even more, having some more common kind of abstraction models for reuse across different environments, as well as like things like reuse of coverage. We want to continue to build our team capability, practice more architectural FPV, some more advanced complexity reductions, and we want to continue to refine our planning, which is really important. Having good experience about where to segment your IP in terms of its verification environments. And one other specific learning that we had was that we felt that architectural FPV would have gotten even better ROI if we had started even earlier in the process than we did. And that's what we plan to do for our next project. All right, so in conclusion, this hybrid methodology, you know, it greatly expands the scope of our formal usage. We got good quality and schedule benefits. We can apply FV and DV each where they're strongest, and we were able to get a lot more members trained up on formal in a real project. All right, thank you for attending my presentation. And at this point, we can take any questions.
Well, thank you, Scott. So we do have some questions, so thank you for sticking around. We only have a few minutes. So what part of the process did the designers co-own during the RTL coding phase? Did they define and write checkers?
Partially. So the designers did work with the formal engineers during this kind of coding and initial bring up phase to define what some of the checkers would be. And they would be closely tied to the design requirements that they wanted to, you know, check during this kind of sanity phase. So yeah, there really was like very close co-ownership of these like basic checkers and constraints in this environment.
All right, thank you. So I think we're over time, and I don't see any more questions on the chat box. So anyway, thank you for sticking around, and our session is coming to a close. And please join me in thanking all the presenters for making this the most excellent session for all the participants. Thank you very much. And on behalf of DVCon, I'd like to thank you all for participating in the event. And unfortunately, we cannot meet in person this year. I hope you all stay healthy and stay safe, and hope to see you live in person next year. So thank you for your support. Bye now.